This is lemma 8.1 from.
Yeah. Yeah, I mean, this is so, yeah. Um, yeah, I mean, this is just, okay, so, uh, mhm. Yeah, okay, let us do this computation. So what we have, um, yeah, so, um, yeah, so at the end, what we want to compute. So we have that G2, yeah, is equal to the sum, yeah, formally -1 or factorial, and here we put the integral, double unification cycle, E1, En, lambda 1, C1, yeah, then we multiply by product P alpha I AI.
Mhm.
Yeah, so, sorry.
Mhm.
Yeah, so yeah, and then in the U variables, this is what, so we just, what we do, we just, um, yeah, so we just take, yeah, the sum, and we take the coefficient of E1 to the power, I don't know, E1, En to the power Tn, yeah, in this expression, in this integral. Um, lambda 1 C1n. Okay. Uh, um, yeah, times uh, the product u alpha I di,
Mhm.
factorial. Yeah, of course. I mean, here sum of di's is equal to 2. So yes, the sum of di's should be equal to twice the genius. So yeah, so why drg? So this is dr1. Dr1
Mhm.
working in genius 1. Yeah, so it is clear, yeah?
Mhm. Mhm.
Okay. Yeah, okay. And then, I mean, yeah, then, just a second.
Yeah. So,
Алло, Юля, я просто разорвалась там, сорка. Я перезвоню. Ладно, да. Yeah, so, okay, and then for this integral, we have, I mean, this expression, yeah, this expression.
mhm. Yes.
So, Yeah. So so this okay. So we will write, and then this is equal to. So first we look at this term, at the first term. Yeah, this one.
Okay.
Yeah. So the coefficient of yeah. Um, Yeah, so we get what we get. So the coefficient of so you see the coefficient of AI squared. We look at the coefficient of AI squared. Yeah.
Okay. Yeah.
Yeah. So So what we have then 1 over 48 sum where I equals 1 to n. Yeah. Then. Formally, how should we do? Yeah, and then the coefficient is this integral. um, how should we? Yeah, formally we should also write sum overall alpha 1 alpha n. Yes. Yes, and then okay, then we write integral over m0 n2 n plus 2 psi I c0 plus 2 j equals 1 to n e alpha j. Then here we write product u alpha I yes, strictly speaking, what we should write? We should write u alpha I 2 times product over j not equal to I u alpha j over n factorial. Yes, so this is so this corresponds to the first term in this expression for this integral. Do you agree?
Yeah.
Then minus. So how should we write this one? Yes, okay, so I just think how to make it. Yeah, okay. Let us write what we have here. So, yeah, so sum. Okay, I just write what we have. I mean, sum coefficient of A1, D1, AN, DN. Yeah, then we have this integral. Yeah, so yeah, and then it's okay. Of course, sum over J. Yeah, or maybe we can make this sum over J here. I don't know. Sum J. J, the coefficient, and then here we write A J squared integral 0 J plus 1 C0 alpha J mu at the mu times at the mu integral M0 and minus value J plus 3 plus 3 C0 G plus 3, yes, and then all this stuff. E new, E J complement, E epsilon E delta. E epsilon delta, yeah, times at epsilon delta. Yes?
Mm-hmm.
Okay. Okay, yeah, and of course times product U alpha I di over n factorial. Okay. Okay. Yeah. Yes. So okay, let us first minus also 1 over 48. Yeah. Here we should also have 1 over. Okay. Okay, let us analyze first the first term that is denoted by A capital. So yeah, first of all I claim that. Yeah, as we often use the symmetry. So here you have the summation from I to n. But yeah, you can actually see that all the terms in this sum, in this term, all the terms are equal to each other. Do you agree? Because you can permute mark points. Yeah, because you see. You have integral over m0 and 2, yeah? Okay, if you can always make permutation, so psi I will go to psi 1. Yes, yeah, and then I mean, since you have summation over alpha j's, overall alpha j's, I mean, since you have this summation, so I mean, the result will be the same.
Ah,
So
okay.
yeah, so I want to say that A is equal to actually 1 over 48 sum n integral m0 and 2. Yeah, so we can n times this integral. So yeah, actually, I mean, here, of course, I have to, yeah, I always often miss some summations. Of course, we should sum over all n, yeah?
Mm-hmm.
Yeah, so I mean, strictly speaking, yeah, so yeah, we have a summation over all n, then n times summation alpha 1, alpha n, and then here we take the integral psi 1, psi 0, and plus 2 j nu, and then here you have u alpha 1, 2, and then here we have u alpha 2, yeah, 0, yeah, so u alpha n over n factorial. Yeah, so do you agree?
Yeah, yeah.
Okay. Yeah, and then I mean, okay, yeah, first, yeah, so yeah, then okay, you can we can this n, I mean, with this n factorial, it reacts with this factorial, we get n minus 1 factorial here.
Okay.
Yeah, and then okay, so yeah, okay, then I can write it like this. So we sum overall n and sum overall alpha. Just I just redenote these alphas. So and then here we m0 n plus 2, psi 1, c0 n plus 2, e alpha, e alpha 1, e alpha n minus 1. So I forgot the matrix. Yeah, so we have to put somewhere at mu nu here, yeah?
Mm.
Okay, and here of course as well. At mu, okay, at the mu, yeah. Yeah, then here we have u alpha xx, and then u alpha 1 over n minus 1 factorial at mu nu.
Mm-hmm.
Yeah, I think I don't forget anything. Yes, but then I mean this is just about, yeah, more or less by definition this is equal to 1 over 48. So you see, yeah, so we have this g ingenious 0 alpha 1 because we take the psi class here and then e alpha here, and then we also differentiated with respect to u mu d squared d u nu at mu nu u alpha xx. Yeah, do you agree with this step?
Okay. Okay.
Okay, so so we get the first term in the desired equation. Yeah, so we want to prove this formula for G2, and we get the first term. Yeah?
Mm-hmm.
Now get the second term. Yeah, so we have this expression for G2. Yeah, so now let us denote the second term by B. Yeah, so I mean this one by B. Yeah.
Mm-hmm.
Yeah, I mean, you see here. So again, I mean, where? Yeah, so we are working here. Yeah, you see. Yeah. So I mean, you see that we take the coefficient of a1 to the power d1, an to the power dn in this in this product of two integrals in these brackets.
Yeah.
But I mean, the second bracket does not depend on a. I mean, yeah, okay, yes. So yeah, so I mean, we can write. Yeah, I suggest to change this bracket. I mean, and put it here. Put it here. Yeah, I mean, this is the same, of course. Yeah.
Uh-huh.
Yeah. Um, yeah. Yes. And okay. How to say it better? Yeah, I mean, again, here we use the same in this formula for B capital. We use the same thing that actually what you see that you sum. Okay, again, so what you have here. I mean, again, sorry. I mean, here we should have the summation over n, of course. So here we have summation over n minus 1 over 48. So 48. Yes, and J is a subset in the set 1n. Yeah, and I want to say that for any J, this sum is the same. I mean, this big sum for any J is the same. Yeah, I mean, this is the same thing that you see. I mean, if you have some subset, then I mean, here, because here under this sum, you sum overall alphas, alpha 1, alpha n. I mean, for any J, you can, I mean, when you take this integral, you can permute marked points and yeah, and see that, I mean, all these integrals are the same for any J. So do you agree?
Okay.
So actually, so how many subsets do we have here? I mean, this is just binomial coefficient, yeah?
Mm-hmm.
So what we can say? We can say that actually the condition was that J, the cardinality of J is greater or equal than to 2. Then we can say that B is equal to 1 minus 48. Minus 1 over 48. Some more n. Some more n. Yes, and then you just sum overall cardinalities of J. Yes, okay. For example, you let us denote this sum overall J greater or equal to 2, less or equal than n. So this is just the cardinality. So let us denote the cardinality of J by J small. So and then I say that for any subset, this sum is the same. So, and how many subsets of fixed cardinality? So, the number of such subsets is the binomial coefficient. Yeah. Mm-hmm. So you write the binomial coefficient n over J. Then you sum. Then you take this sum overall alpha 1 alpha n. Yes, and then here you choose J, some J that we some fixed J. So here we will take J capital to be 1 J small. So we will get coefficient of A1 or T1 n. And here we have A1 plus A J squared integral M0 J plus 1 J plus 1 C what we have C0 alpha J small times E mu. So then add the mu nu times the integral M0 over M0 n plus 3 minus J small C0 3 n plus 3 minus J small. Yeah, then all this E nu, and then here we have EJ plus 1 E, oh sorry, E, not EJ plus 1, E alpha J plus 1. And then E alpha n, E eta, E delta, eta epsilon delta. So yes, and then also the product times the product U alpha I di over n factorial. So do you agree with this step?
Okay.
So yeah, basically we just chose one subset, one fixed subset J. Yes, and then said that okay for or for any other subset, I mean the result is the same. So and yeah, we multiply it by the binomial coefficient. Yeah.
Okay.
Okay. Yes. Yes, and then I mean, what can we do? Yeah, first let us denote this binomial. Let us just write explicitly the binomial coefficient. So this is n factorial over j factorial over j factorial n minus j factorial. Yeah, so n factorial. Yeah, and then we see the cancellation. Yes, so n factorial. Yeah, cancels this n factorial. Yeah. Yeah. So yeah, is it okay? Yeah. Okay. Yes, and then I mean, actually, what we wanted to split this sum. Why? Because what? Yeah, you see, here we have. I mean, we want to take the coefficient of a1 to the power d1, an to the power dn of this expression. But this expression depends only on a1, aj. Yes. So actually, here you can you don't have to have monomials. You don't have to have monomials depending on all a1, an. So it can only depend on a1 to the power d1, aj to the power dj. Yeah.
Yeah.
Okay. Okay, and then you actually see that all these. I mean, you see that. I mean, we have. I mean, the sum splits. So, so this sum, I mean, splits in two terms. I mean, splits in the product of two. I mean, independent expressions. So, you have 1 over O. 1 over 48. Okay, let us in this sum let us denote L, the difference n and j. So L is n minus j. Yeah.
Okay.
So actually we get the following. So we get that. Yeah, and here this product alpha I di. How can you write? You can write it in the following way. So this will be just the product u alpha 1 d1 u alpha j dj over j factorial, and then the u alpha j plus 1 u alpha n over n minus j factorial. Yes? Yeah, because I mean we see that, yeah. So I mean the coefficient, this coefficient, I mean the monomial cannot depend on aj plus 1 an. So we have use u alpha j plus 1 without any derivative. Yeah. So and then the result splits. So we have minus 1 over 48. And here we write sum k. Not k, j, small j greater or equal to 2, L greater or equal to 0. Yes, and then yeah, it splits. So we write a sum alpha 1 alpha j, yeah, d1 dj, coefficient of a1 to the power d1 aj to the power dg of this expression. And then we take this integral G plus 1 E alpha G E mu. Yes. Yes, and then you take U alpha 1 U1 U alpha n, not alpha n, alpha J dj over J factorial. So this is the first.
Okay.
Then times at the mu nu and times the second. So and here you have sum. And then we can write beta 1 beta L integral over m0 n not
L
n.
plus 3.
Yeah, L plus 3 E C0 L plus 3 E nu E beta 1 E beta L E epsilon E delta eta epsilon delta, and here we take then U beta 1 U beta L over L factorial.
Okay.
Yeah, and then you can immediately see that the second term, term is equal to what? This is just what you take. Yeah, G. How to say G0. Yeah, and then you take the G. What you take? Yeah, you take the derivative. Yeah, because you these indices they run and these indices are fixed. Yeah.
Mm-hmm.
So you should take the third derivative. Du nu du epsilon delta eta epsilon delta. So yeah, but I think we just I mean in this paper we denoted G0 by F. Yeah.
Mm-hmm. Yeah.
So we see that again. We see yeah, part of the expression that you want to get. Then it remains to look at this integral, at this one. Yes.
Mm-hmm.
So yes. Yeah. So what we want to understand this thing. So yeah, this is actually very simple thing. How to say it? Maybe we had. Maybe. Yeah, actually, I mean, this is a very simple thing. I mean, I just want to understand how to explain it in a better way. Yeah, okay. So what we want this thing. We want this thing. the sum of row alpha 1 alpha j, yeah, sum over j, alpha 1 over j, d1 dj, yeah, the coefficient e1 to the power d1, a j power dj. Yeah, I mean, yeah, I think it's better just to what? Yeah, just to go in the p variables. So I mean, it would be better to a j squared. We have integral m0 j plus 1 c0 yeah. Yeah, this expression, yeah, times the product u, yeah, u alpha 1 e1 alpha j dj over g factorial. Yeah, but then let us go to the p variables again. To the p variables. So what we will get? We will get that this is sum over j. Yeah, minus 1. And then you get sum a1 plus aj. I mean, I forgot to write. I mean, when I wrote at the beginning. Yeah, when I wrote, no, this is fine. Yeah, this is fine. So we write sum a1 plus aj squared integral m0 j plus 1 okay, blah blah blah, this integral. Okay, I write it. Let's see. New. And then we take p alpha 1 a1, p alpha j aj over j factorial times e to the power I a1 plus aj x. Yes? But then you see that yeah, actually it would be maybe better to write this sum squared here. A1 plus an squared. Yes. But then you see, I mean, this thing is just dx squared applied minus dx squared applied to exponent I a1 plus a gx. Yes?
Yes.
So, yeah, well, I mean, this is not very, I mean, the discussion is not so short, but yeah, then this a1 plus aj squared corresponds to the second derivative. So, and then you get what? So you apply dx squared to what? To sum over rho j. Or maybe actually, yeah, maybe I should use this, just copy. It would be better. Yes. So what we have? we just have the same expression, a1 plus an x sum over j dx squared. Yes. But then, I mean, you see that this expression is equal to what? I mean, again, you integrate over m0, c0. So this is just what? This is just g0, d. So mu is fixed. So du mu, df, du. Yeah. So in total, we get is equal to dx squared df du mu. Okay, and then we just collect everything. Yeah. So what we get? We get that g2 is equal to a plus b. Yes. So where a a is this integral. A is the integral over this expression. 1 over d squared g 0 alpha 1 du mu u alpha xx minus 1 over 48 dx squared df du mu at mu and then here we have the cube, d cube f du mu du epsilon du delta eta epsilon delta dx. Yes, and I mean yes, and then at the end, for some reasons, in this paper we just move dx to the other term. We can move it here. So, So then write that. This is equal to integral 1 over. So. So just move this dx to here, dx squared here, dx squared, dx. So this is the formula that we get. What do you think? Is it is it clear?
Yeah, it was more elaborate than I thought.
I mean, you see, just I mean, I understand that. I mean, it requires some. I mean, it requires some experience, because when you after some time, you will be able to, I mean, to make this step quickly. Yeah, I mean, yeah, the detailed explanation. Yeah, you see, it's not so short, but yeah, okay. So yeah, so this is the explanation. Yeah.
Okay. Okay. Yeah. Yeah.
Yeah. So is it all that you wanted to ask?
Yeah. 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 I mean, because yeah, I think it was the last step missing from the other proof,
Okay.
the identity, and yeah. So yeah, I went to this other paper that I suggest uh, to take a
Mm.
look for it, but like yeah, I kind of see like where did the derivatives came from, but yeah, I mean now I see that it's more elaborate, elaborated. Yeah. Yeah. Okay. But yeah, thank you.
Yeah. Okay. Good. Yeah. By the way, yeah. After this interview, this transfer interview,
Uh huh.
yeah, I mean, yeah, Vincent and Joao mentioned that there is some formal thing that you should or somebody should, maybe I or maybe Oleg, to enter some meetings in this grad system.
I did already.
So you did it, yeah?
Yeah, I did it like I don't know if it was like 2 weeks ago or something like that. Yeah, I updated all the meetings until the mid August, I think.
Okay, good.
Yeah, yeah. So we have a yeah, we're updated. I mean, I just need to record. I try to record it like every 2 weeks. Oleg mentioned that it was only record once per month, but
Uh-huh.
I decided
Okay.
to record like every 2 weeks. Yeah, actually, I'm already late for the last time.
Mhm.
So this weekend I will write a report for the end of uh, August and mid September.
Okay.
But I think I mean I submitted them, but it said the system records that you need to approve them.
I need to approve them.
Yeah,
Yeah.
it says
Okay.
that waiting for operation from Alexander.
Okay.
Yeah.
Okay. I will try to yeah to do. Okay. I will try to. Yeah. I mean, yeah. I called IT department and they said that yeah that my account should be should work, but yeah, still it doesn't work.
Mm.
Okay. I will call them again. Yeah. Okay.
I mean,
What about
uh
what about your teaching? So I mean, yeah, not teaching. I mean your courses. So did you say that you are done? So
yeah,
everything
yeah. I finished all the credits for yeah.
nice. Okay. So now you just can fully concentrate on your research. Yeah.
Yeah.
Okay.
I
That's
also
nice.
need to like I would like to learn more advanced things on algebraic geometry.
Uh-huh.
Uh, so I'm still trying to look. I mean, I'm trying to follow this Harris book,
Uh-huh.
and it's good because I found solved exercises, so I can get myself started to see like how the proofs work and yeah.
Okay. Good. Yeah, that's good, of course. Yeah, to understand this algebraic geometry better. Yeah. Okay, good. So, yeah, should we schedule the next meeting on Tuesday?
Okay,
Yeah, okay. This is the same time, yeah?
okay, yeah,
Okay, good. Okay, yeah, then yeah, see you on Tuesday.
okay. Thank you very much.
Yeah, thank you.
Bye.
Yeah, bye-bye.